Hello everyone, welcome to chapter 15, Kinetics of a Particle, Impulse and Momentum. This module is going to cover impact under the principle of impulse and momentum. The objectives is first to understand and analyze the mechanics of impact, and from there we're going to analyze the motion of bodies undergoing collision in central cases of impact. There are two types of impact. This module is going to cover central impact. Impact usually occurs when two objects or two bodies collide during a very short period of time, causing large impulsive forces. So these are large forces that are happening on a very short period of time, but because they are large, they give you large impulses. And these forces are exerted between the two bodies on each other. Common examples of impact are a hammer striking a nail, you could have a bat striking a ball, and so on. Or you could have even two cars hitting each other. The line of impact, this is something that we are going to use this definition a lot in our analysis. The line of impact is a line through the mass centers of the colliding particles. So whenever you have two particles, connect the two center of masses together with one straight line. This line is called the line of impact. Now, this line is going to be used to differentiate between two types of impacts, central impact and oblique impact. This module, as I mentioned, is going to discuss only central impact. So let's discuss the mechanics under which central impact happens. Imagine that you have two balls or two objects or two particles as shown on the figure on the right. So if the central impact occurs, that means it is an impact case when the directions of motion of the two particles are along the line of impact. For example, in this case, I know that this is the center of mass for the first one, this is the center of mass of the second one. Let me connect the two. So this line is my line of impact. Now, look at the two objects, and it has to be both of them, not just one of them. Both objects or particles, they have a velocity that is acting on the same line of impact. In this case, we call it central impact. If it happens that the line that connects the two centers of masses, which we call the line of impact, is not the same of at least one of the two particles' initial velocity. As you can see, this one has an angle theta, this one has an angle phi, for example. So in this case, we call this oblique impact. We are only going to discuss central impact in this case. Okay. Now, central impact happens when the velocities of the two objects are along the line of impact, as we mentioned. Once the particles contact, they will start deforming if they are not rigid, and energy in that case will be transferred between the two particles, which will make the final velocities different than the initial velocities. Now, we need to convert this into actual equations. So let's look at the different stages of impact. First of all, you have the condition for collision. You have two particles. Each one has its own linear momentum, okay, MAVA1, and you have MBVB1. Impact will happen when velocity of A is greater than B, and I am considering the sign as well. I could have B greater in magnitude than A, but it has a negative sign, so it is traveling towards particle A. Anyway, so you get the point that it has to be a velocity greater than the other, so A and B will collide. Now, once they hit, at the instant they hit, as you know from principle of impulse and momentum, there will be an impulse acted from A on B, which is integral of P dt, and there is an opposite but equal value of an impulse from B on A. Okay. Now, once these impulses will happen, from conservation of momentum, because these two are equal and opposite, I'm going to have now a stage where maximum deformation happens, where the two velocities are the same. So the two objects will move with the same velocity. Now, after this, energy will transform, kinetic energy will transform between the two and it will change. And then you get a restitution period where they will start to separate. Again, there will be separation impulses. Each one wants to push the other particle away, and they're equal in magnitude, opposite in direction. And finally, you get the separation period where each one is going to have a new linear momentum, different velocity. And B will be more than A. And simply think of example where you have a car driving slowly and you have a car that is traveling at a higher speed and it hits the first car. What happens with the slow car that it will get energy, so it will travel faster, and the car that was traveling at a high speed will slow down after the impact. And this is basically the case. So let's derive the equations. The first thing, we know that I can apply conservation of linear momentum from the moment just before impact till the moment after the impact. So I'm going to have MAVA1 plus MBVB1 equals MAVA2 MBVB2. And I'm writing this as a general conservation of linear momentum. I'm not considering the signs. You have to look at the sign in your problem. You have to decide if you want right is positive, upward is positive, and so on. And based on that, you can decide the velocities of each of these. Now, in most problems, the initial velocities of the particles, VA1 and VB1, are usually known. This is something you know at the beginning. Most of the cases, we need to find the final velocities, VA2 and VB2. Now, this is one equation, and I have two unknowns, two velocities. Therefore, I need another equation. So, the other equation comes from principle of impulse and momentum, and we use it to develop this equation, and we get something that is called coefficient of restitution. What does this coefficient of restitution represent? Basically, it represents the amount of deformation then separation of these particles. How much, for example, think about a tennis ball. You have two types of tennis balls. When you throw it to the ground, they might bounce at a different height. That's because of the coefficient of restitution of each ball. So how do we derive it? First of all, let me go back to the figures that we were discussing. I'm going to start from this case 1. I will include case 2, and then I will end up with case 3. Okay? So I will take particle A and B before the impact, and then at number 2, where the impulses will start acting, and then 3 when they have maximum deformation and they move together with the same speed. What we're going to do is that I'm going to write the two equations. The first one, it's going to be MAVA1. I'm only looking at A, by the way. I'm not considering B. So it's going to be MAVA1 minus, if you can see here, I'm looking at the impulse acted from B on A. So it's going to be minus delta P dt, integral of P dt, sorry. So it's going to be MAVA1 minus integral of P dt equals MAV. And I say V because it is a shared velocity. And then I can do the same thing going from case 3 to 4 when the restitution impulses will start acting, and then 5 when they separate. So I'm going to write the same thing. So now, the initial velocity at stage number 3 is the shared velocity minus integral R dt because it is B acting on A, and then I have MAVA2. Now, coefficient of restitution is going to be defined as the ratio of the restitution impulses over the acting impulses, the impact impulses P. Once you do it, you get this expression. You can do the same thing for B. You will get this. Taking V outside of this, just substituting B for VB2 and VB1. Finally, you get this final expression. Just to have it clearly written here. So E equals to the final velocity of B minus final velocity of A over initial velocity of A minus initial velocity of B. Keep in mind, it doesn't have to be B. It could be A minus B. It's just two particles. The point is, you have final velocity in the numerator. You have initial velocities in the denominator. plus if you're starting with particle B minus A, then it has to be in the denominator A minus B. That's what matters. Now E, coefficient of restitution, has a value between 0 and 1, and it has two limiting conditions. The first one is elastic impact, where E equals to 1. This is the most perfect elastic case. Usually in reality this is not realistic, because this means there is no energy loss, and the separation the relative separation velocity equals the relative approach velocity. So this is a very ideal situation. Plastic impact, where E equals 0. This is a plastic impact where relative separation is 0. That means they start deforming together and they stick together. So E usually is something in between. Now, in some cases, when you solve these problems, since we discussed coefficient of restitution, we talked about energy losses. That's why E cannot be equal to 1, and so on. So in some problems, we might be asked to find the energy losses. Since you know the initial velocity and you calculate the final velocity, then basically you can say delta T2 minus delta T1 should give you the energy losses, where T, if you remember, equals half mv squared. This is the kinetic energy of the particle. Now, in some cases, students make the mistake that a problem will start where the initial velocity given in the problem is not the velocity before impact. For example, I could have an object thrown from the top of a building, and then I give you that velocity that it was thrown with. And then when it reaches the ground, it will hit another object. So the initial velocity at the top of the building is not your initial impact velocity. Therefore, keep in mind that you can use things like conservation of energy, or even kinematics like projectile motion and so on. These things will help you to get initial velocity if needed. Now, the main two equations that we have for this module are conservation of momentum and coefficient of restitution. You solve these two to get to unknown velocities. So let's start with the first example. Now, the slider block B is confined to move within the smooth slot. So it's moving horizontally, smooth, there is no friction. It is connected to two springs, each of which has a stiffness of 30 Newton per meter. They are originally stretched 0.5 meters when S equals 0. S, as you can see in the figure, is going to be the horizontal displacement, the horizontal movement. And it says here that the two springs are originally unstretched at this location. Sorry, not unstretched. So at this, they are originally stretched amount of 0.5. Yes, the length is shown as being 0.2, but you already have the stretched amount, which is 0.5. And we'll come to this when we solve the problem. Determine the maximum distance S max where that block B moves after it is hit by block A, which is originally traveling at VA equals 8 meters per second. Coefficient of restitution is given as 0.4. The mass of each block equals 1.5 kilogram. Also determine the average net force acting between blocks A and B during impact if the impact occurs in 0.005 seconds. So let's start with the first part, which is we need to find S max. Before I find S max, I need to find the velocity of block B after impact. Now, this is smooth, so there is no friction forces. The force of the spring is neglected because we are discussing the case 1 before impact, and 0.2 is just as A reaches block B and hits it. So this is my case 2. So we start with conservation of momentum. I'm going to say to the right is positive, and we have summation of mv1 should equal to summation of mv2, depending on each object. So I'm going to have ma, which is 1.5 times initial velocity 8 meters per second, plus block B was at rest, so it's going to be 0. This should equal to 1.5 VA2, which is unknown, plus 1.5 VB2, which is unknown. And this is equation 1. Now I can do coefficient of restitution. Again, to the right is positive, just to remind you. E was equal to, you can start with block B or A, does not matter. First of all, you take the differences of the final velocities over and you switch the two particles, difference between initial velocities. Okay? So it's going to be VA1 minus VB1. Okay? So this gives me, I'm going to substitute the values that we have. It's going to be 0.4 should equal to final velocity of B is unknown minus final velocity of A is unknown over, this is given as 8 minus 0. So this is the second equation. Now you have two equations, two unknowns. So solving 1 and 2 basically gives me the final answer, where VA2 equals to 2.4 meters per second and VB2 equals to 5.6. Okay, now I have the initial velocity of B, the final velocity of B. Now let's think about this problem. It asks you to find the maximum distance traveled, S max, before block B, after block B moves, after it is hit by block A. Okay, so it is confined by the spring, so it has a certain amount it will stretch. So let's look. What kind of force is acting here? I only have the spring forces, and I have initial velocity of B, and I need to find distance. Now, the theory that covers velocity with forces and distance is either principle of work and energy or conservation of energy. So we're going to apply conservation of energy between point 2, where B will start moving, until when it reaches S max, and we're going to call this 3. Okay, so let's start with this. I'm going to write the principle. So I have T1 plus V1 should equal to T2 plus V2. And remember, I have no weight here, I only have the spring force. So T1 of block B should equal to half M, which is 1.5, V squared, which is what we just calculated here. So it's going to be 5.6 square, plus I only have the spring forces. I have two springs. They are identical, the same spring stiffness, and they have the same amount of stretching. So kinetic energy for the spring, if you remember, first of all, I have two of them. And kinetic energy was half Ks squared. So it's half K, which is 30. And S, if you remember, and I always say that this is one of the sources of confusion to students, S is the current length minus the unstretched length. So it is the amount of stretching or the amount of compression at the current stage, which is already given to me in this point as 0.5. No need to calculate S as something minus something. It is already given to you. This should equal to, now S max means this is the maximum distance block B will travel before the springs will have to pull it back. Therefore, its final velocity is going to be 0. Okay, plus I have two springs. It's going to be half K, which is 30. And now let's look at S. It's going to be something at this point. So this is 2 given to me. This is S max. So this has to be square root of 2 square plus S max square. Okay, so this is the current length at this point. So this is the current length. In order to find what is S, so it's going to be the current length, which is 2 square plus S max square under square root minus the unstretched length. What is the unstretched length? Well, at position 2, this is equal to 2, and I was told that it was originally stretched 0.5. So unstretched becomes 1.5. So I'm going to take this and apply it in here. So it's going to be half times 30 multiplied by square root of 2 square plus S max square minus 1.5. Okay, everything is known in this problem except for S max. If you carry out the calculations, you will get that S max equals 1.53 meters. And this solves the first part of the problem. Now, the second part says determine the average net force between block A and B during impact if impact occurs in 0.005 seconds. So, in order to do this, you have to take either block A and put the impulse of B acting on A, or take block B and include the impulse of A acting on B. You can solve it with each one of these, it does not matter. So we are going to take block A in this case. So right is positive. I will apply principle of impulse and momentum. So I'm going to say MA VA1 plus summation of F dt should equal to MA VA2. Now what I have, the mass is 1.5 multiplied by initial velocity 8. Now B will act on A, so it's going to be opposite, so it's going to be minus, I don't know the value, so I'm going to say it asks you to find F average, so I'm going to write F average times the time, 0.005 seconds, equals to, mass is 1.5, and VA2 was calculated from the previous case as 2.4. This should give you an answer that F average, the average impulsive force, equals to 1.68 kilonewton. Now, as I mentioned before I started solving this part, that you can solve it either by doing block A or by doing the same thing for block B. So if you do MB VB1 plus F dt equals to MB VB2, you do this, you have here 0 plus F average times 0.005 should equal to 1.5 times final velocity of B, which is 5.6. This should give you the same value exactly, and in this case it does, and it's equal to also 1.68 kilonewton. Now, this covers a lot of ideas. You are using impulse and momentum, you are using conservation of energy, and you are using also central impact problem. So this is a very good example to practice on this theory. Next module, I will discuss oblique contact, which also oblique impact, which also covers many of the ideas that we discussed in this module. I hope that it was useful and helpful to you, and I wish you the best in your studies. Thank you.